Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is section 1.8, which is on combinations of functions. Specifically, well, more importantly, composite functions. All right. So before we talk about composite functions, let's talk about arithmetic combinations of functions. All right. So let f and g be two functions. Right? Then we can say that their sum is defined by f plus g of x, all right, which is just really saying f of x plus g of x. All right, so that's a sum of two functions. The difference would be f minus g of x, which is just f of x minus g of x. All right. The product would be f times g of x, which would just be f of x times g of x. All right. And that was supposed to be the third. The fourth is the quotient of two functions, which is f over g of x. Now this is defined to be f of x over g of x as long as g of x does not equal 0. All right. Now, so those are all the arithmetic combinations. In here, I'll make a note. The domain of these is the intersection of the domains of f and g. With the exception here, you also have to remember that g of x cannot be equal to 0. All right. But otherwise, the domains is just the intersections of the domain of the combination is the intersection of the domains of each of them separately. All right, so let's get some examples in here. So let f of x be equal to x squared minus 1 and g of x be equal to y minus x. All right, and we're going to find the following. So first I'm going to say what is f plus g of x. All right, and in here, well, what would that be? F plus g of x would be, well, we know by definition this is really f of x plus g of x, which would be x squared minus 1 plus y minus x squared, which would give us, well, x squared plus a negative x squared. Oh, hold on. Where did I get that extra square from? There we go. X squared minus 1 plus y minus x. Make sure you copy it correctly. So we have x squared and then minus x, and then the negative 1 plus 1 cancel each other out, so we end up with just x squared minus x. So if I said, for example, what is f plus g of 2, we can just go ahead and plug it into the bottom part here, the simplified version. So we have 2 squared minus 2, which is 4 minus 2 is 2. All right. Next one. Let's say that I asked for f minus g of x. All right. Well, that would be, by definition, f of x minus g of x, which is just x squared minus 1 minus y minus x, which would then be, well, x squared minus negative is plus, so x squared plus x, and then negative 1 minus 1 is negative 2. So that's our simplified version. And similarly, I can say, well, what would f minus g of negative 3 be? Right, so we would say we have negative 3 squared plus negative 3 minus 2. Negative 3 squared is 9. 9 minus 3 is 6. 6 minus 2 is 4. All right. Next one. So that was the sum and the difference. Let's look at the product. Let's say that we have f times g of x. Well, remember this is just f of x times g of x, which if you recall, f of x was x squared minus 1, and then g of x was y minus x. So if we FOIL this out, we end up with x squared minus x cubed minus 1 plus x, which we don't really like that order. We'll rewrite it as negative x cubed plus x squared plus x and then minus 1. All right. All right. So now, let's say that I said, what is f times g of negative 1? All right. Well, we just plug it into here. We have the negative of negative 1 cubed plus negative 1 squared plus negative 1 minus 1, which gives us, well, negative 1 cubed is negative 1 with a negative 1 in front. It's a positive 1. And then negative 1 squared is positive 1. And then minus 1 minus 1, which gives us 0. All right. Overall. So that's f. So that was a product. Now let's look at the quotient. Let's say that I have f over g of x. Well, this is really just saying f of x over g of x, which in this case is x squared minus 1 over y minus x. Now remember, what we want to do here is we want to simplify, so let's factor the top, x plus 1 times x minus 1, right, because it's a difference of squares, and then we have that over y minus x. Notice here that these two are just equal to negative 1, right, because they're negatives of each other. Let me circle that better. There we go. Those are just equal to negative 1. So what we really have here is just negative 1 times x plus 1, which is negative x minus 1. All right. And let's say that I have f over g of, or that I asked for f over g of 1. Then we would say, well, just like before, just plug it into the simplified version, and we have negative, well, not negative x, negative 1 minus 1, which is negative 2. Now, that's wrong. Why is that wrong? We follow the same exact thing as we did on the other ones. Well, let's remember something. Let me scroll up so you can see it. The domain was the intersection of f and g, but also you cannot include the values that make the denominator 0. If you look at g of x, 1 makes g of x 0, right, from here. So, in other words, we wouldn't have been able to plug 1 into this statement because it would have made the bottom 0, right? 1 minus 1 gives us 0, so we can't plug it into the simplified version either. So it turns out that this is wrong, and the correct answer here should be undefined, or no solution. Undefined makes more sense because it is not defined at that value, all right? But what if it was something else, any other value? So let's say, for example, f over g of 2. Well, that I can certainly plug it into the simplified version because, well, it would have been fine in the original version, all right? So we have negative of 2 minus 1, which gives us negative 3, all right? So you gotta be careful about situations like this. Now, that was arithmetic combinations of functions. Let's talk about composite functions, all right? So composite functions. And in here, well, let's get a definition for what a composite function is. The composition of the function f with the function g is given by, so f composed with g of x, alright, which is defined to really be f of g of x, alright. So this is read as f composed with g of x, and over here f of g of x. Okay, so the domain of f composed with g is the set of all x in the domain of g such that, well, let's make that look as such. There we go. Such that g of x is in the domain of f. All right. So in here, essentially what we're saying is, whatever value we get after we plug in x into g, we should be able to still plug it into f. All right. That's what this is essentially saying. So we have to take the domain of the inside function and then make sure that whatever our output is still within the domain of the outer function. All right. The inside function being g of x, the outer function being f. So let's do some examples. Given f of x is equal to 2x plus 5, and g of x is equal to 4x squared plus 1, find the following. All right. So here we go. So example J. Let's say we were asking for f composed with g of x. All right. Well, what is that? By definition, this is really saying f of g of x, right? And then we know that whenever we have something like this, whatever's on the inside here needs to be plugged in into the x. So this is really saying 2 times g of x plus 5. And then what's g of x? By definition is 4x squared plus 1. So this is 2 times 4x squared plus 1, and then we have that plus 5. Distributing this 2, I get 8x squared plus 2, and then that plus 5, giving me a final answer of 8x squared plus 7. All right. Now, that's not the only way to do this kind of problem. I'll do an alternative version here. So we already know that we have f of g of x, right? We could also go ahead and plug in g of x at this point. So we have f of 4x squared plus 1. And then we know that, well, whatever's inside here is supposed to replace the x. So we have 2 times, plug this into the x, 4x squared plus 1, and then that plus 5, which at that point, we know what that gives us, right? Same exact thing as this line. So that's another way of thinking about it. I personally like to just put in the g of x and then afterwards plug it in. All right, so that's f composed with g. Let's look at g composed with f. Well, g composed with f is really saying g of f of x, right? So that's really saying plug in f of x into g. And what was g? 4x squared plus 1. So I'm going to say what we have here is 4 times f of x squared, and then that plus 1. But then what was f of x? F of x was 2x plus 5, so we have 4 times 2x plus 5 squared, and then that plus 1. Let's continue. We have here 4 times, expand this, we're just foiling it, so we have 4x squared plus 20x plus 25, and then that plus 1. Distribute the 4, 16x squared plus 80x plus 100, plus 1, right? Distributing that, giving us a final answer of 16x squared plus 80x plus 101. All right. What I want you to notice here is that right away we see something. I want to make a note here. Our final answers were different, right? They were different. So in general, I'll make the note here. Note. In general, f composed with g of x does not equal to g composed with f of x. All right, and that's an f. And you clearly see that here, right? We had two different answers for f composed with g and g composed with f. All right. Now, so that's k. L. Let's say that I have f composed with f of x. Well, this is really saying f of x, right? And that's really saying plug in f of x into f. All right, so let's remember what f was. It was 2x plus 5. So since I need to replace f of x with every x, I have 2 times f of x plus 5. And then now to replace this f of x, well, that was 2x plus 5. So we have that plus 5 again, giving us 4x plus 10 plus 5, which is 4x plus 15. All right. So that was f composed with f. Next one, m. Let's do g composed with g. Well, what does this mean? This means g of x, which is saying plug in g of x into g, right? So what we really have here is 4 times gx squared plus 1, right? That was g of x, 4x squared plus 1. So we just plugged in g of x wherever we have x. And, well, now we need to replace that. So we have 4x squared plus 1 squared, and then that plus 1. Expand this, so we end up with 16x to the 4th plus 8x squared plus 1, and then that plus 1. Distribute the 4. 4 times 16 is 64, so 64x to the 4th plus 32x squared plus 4 plus 1, and finally just combine like terms. This is x to the 4th plus 32x squared plus 5. All right, so that would be g composed with g. All right, so that's in general how to compose two functions with each other. Now, let's talk about how to find their domains. Example n. Let's say that I have f of x being equal to 1 over x minus 2 and g of x being equal to the square root of x. And I said find the domain of f composed with g of x. All right. So in here, well, we're going to be working with a composite function. So we first need to find the domain of the inside function and then the domain of the outside function. All right. Recall that the domain of a composition was a set of all x in the domain of the inside, such that the inside function g, such that g of x is in the domain of f. All right. So first, domain of inside function. So we're looking for the domain of g of x. So in this case, what's g of x? So g of x was the square root of x, right? And for that, we have to have, let me write it this way. G of x was the square root of x. And for that, x must be greater than or equal to 0, right? That is the domain of g of x. All right, cool. Second, we're going to find the domain of the composition. All right. And what was the composition? Well, the composition f composed with g of x was f of g of x, which in this case really means 1 over g of x minus 2, which really means 1 over the square root of x minus 2. And in here, well, we've got a fraction. And how do we find the domain of a fraction? Well, the domain of a fraction is its denominator, the square root of x minus 2, cannot be equal to 0. So in here, we're going to say, well, the square root of x cannot be equal to 2, so that x cannot be equal to 4. All right? So that is the domain of the composition. So now we need to take the intersection of these two statements. X must be greater than or equal to 0, and it cannot be equal to 4. So what does that mean? Let's think a bit on the number line. Greater than or equal to 0, so that means we're allowed to include 0, and we're going to the right. But we cannot include 4. But all the other numbers are fine, all right? 4 is the only one that's not okay. But everything between 0 and 4 is fine, including 0. Nothing to the left of 0 because, again, x must be greater than or equal to 0. All right. In interval notation, what would this be? This would be starting at 0, going to 4, union starting at 4, going to infinity, not including 4 or infinity. All right. But we are including 0. All right. So that was n. Let's say that I said find the domain of g composed with f of x, right? And we're going to be using the same functions f and g. I'll remind you what they are. Let's see. F of x was 1 over x minus 2, and g of x was the square root of x. So we're going to find the domain of g composed with f. Okay, so remember, first we're going to find the domain of the inside function, which in this case is f of x. And f of x was 1 over x minus 2. All right, and for this, what's the domain? Well, we've got a fraction. With fractions, the domain is that the denominator cannot equal 0. So in here, x cannot be equal to 2. And then we need to do the domain of the composition, g of f of x, g composed with f of x. Right? And recall that that was g of f of x. And what is that? Well, that says plug in f of x into g. So we're going to plug in f of x into g. So we've got the square root of f of x, which really means the square root of 1 over x minus 2. All right. Now, in here, well, we've got a square root function, right? In a square root function, the inside must be greater than or equal to 0. All right. So in here, well, we've got a fraction equaling 0, right? Well, let me rephrase that. This splits up into two statements. 1 over x minus 2 must be greater than 0, or 1 over x minus 2 must be equal to 0. All right, because of the or. Now this one over here, 1 over x minus 2 equals 0, is not possible because we've got a fraction equaling 0. Whenever we have a fraction equaling 0, the only possible way for that to happen is if the numerator itself is equal to 0, but our numerator is 1. So in here, this is not possible. So we have to check the scenario over here. All right. Now in here, we've got a fraction. We want that to be greater than 0. The top is already positive. So that means the bottom must also be positive, right? For this fraction overall to be a positive fraction, a positive value. So in here we have x must be greater than 2, right? By moving the 2 over. So now we've got two things. From the first part, x cannot equal 2, and x must be greater than 2. Okay? So in here, well, what does that give us? Here's 2. We have to be greater than it, and we cannot equal it. So there we go. All right, that would be our number line. In interval notation, that would be starting from 2, going all the way up to infinity. And notice that these domains were different, all right? We were using the same exact functions, but we were composing them differently, right? In the first one, we were doing f composed with g of x, and it was everything including 4 and up, including 0 and up, excluding 4. Whereas over here was just everything above 2. All right. All right. So now, in order to work with composite functions correctly, we want to be able to see what is the inside function and what is the outside function. All right, that is called decomposition of a composite function. All right, decomposition of a composite function. All right, so essentially here we want to think to ourselves two questions. What is the inside function? And the second question is, what is the outside function? All right, which one's the inside function, which one's the outside function? All right, so, and what do I mean by that? Well, let's say that we had some function h of x, and we want to rewrite it as something like this: f composed with g of x. Right in here, we're gonna have f of g of x. So what I'm getting at is, I'm gonna give you some function h of x. We want to figure out which one's f and which one's g. All right. So I guess I should say here, given this, find f and g. All right, find f of x and g of x. So we were at example P. So let's say h of x was something like 1 over the square root of 3x plus 1. All right. And there could be multiple correct answers. All right. So one possible solution for this, what would it be? Well, I can see that here overall I've got a fraction, right? So I can say that, for example, the outside function could be the fraction, 1 over x. And then the inside function could be, well, the denominator, the square root of 3x plus 1. All right. So that's one possible solution. Solution 1. Let's look at a different solution. Solution 2. All right. We can say, for example, that f of x is 1 over the square root of x, and that g of x is simply 3x plus 1. All right. That also works. These are equivalent solutions. All right. Let's look at another one. Let's say that I had h of x being equal to the cube root of 8 minus x over 5, right? And let's look at some possible solutions in here. Solution 1 would be, well, if f of x were, well, again, I see a fraction, so I could say something like x over 5. And in this case, g of x would be the entire numerator, the square root of 8 minus x, all right? Another possible solution, solution 2, would be, let's say, for example, f of x were the cube root of x over 5. And then g of x being the inside function would be just 8 minus x, right? Let's look at one more example. Example R. Let's say that h of x were something like 1 over 2x plus 3 to the 4th, all right? And again, here we're going to look at a different solution. Solution 1. F of x, well, what do I see? I see I have a fraction, so I could say something like f of x is equal to 1 over x, right? And then g of x could be equal to then the entire denominator, 2x plus 3 to the 4th. Let's look at another solution. We could say something like f of x is 1 over x to the 4th, right? And g of x could simply just be 2x plus 3, right? So yeah, so here, the thing to note here is that we can have multiple solutions for what what the composition for h is, all right? And both of these solutions work. All of these solutions work. All right, so that is the end of 1.8.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, You don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.